Okay, we are going to look at writing out a total and a net ionic equation for a double replacement reaction. Actually, a specific type of double replacement reaction, we call it a neutralization reaction because it happens between an acid and a base, but everything is the exact same as what we've done before. The two positive ions trade places. So on our product side, the sodium is going to be paired up with the sulfate ion. Sodium's a +1, sulfate is a -2, so we need two sodiums in that compound. Hydrogen is going to be paired up with a hydroxide ion. I write it as HOH just so you can see where those two pieces are coming from, the H from the acid and the OH from the base. But it is the exact same thing as water, so you can also write it as water. Water is always going to be a liquid, so there's my L for it. And looking at our solubility rules, sodium sulfate is aqueous. Last thing we need to do, at least to write out this molecular equation, is to balance it. I have two sodiums on my product side, so I'm going to need a 2 in front of the sodium hydroxide. And now that gives me two OH groups and two H's from the acid, so I need a 2 in front of our water. Now we can actually begin the problem of writing out our total and our net ionic equation. This also is review from our unit 3 in this class, our types of reactions unit. If you remember back to that unit, we take everything that's aqueous and we split it up into the ions that make it up, because they really exist as split up ions in that solution. So if we looked at H2SO4, we're really going to form two H+ ions. We write that they are aqueous because they're in water, and that sulfate will stay together because it's a polyatomic ion. So moving that as SO4, acting for the charge, and I write aqueous. Now, looking at our sodium hydroxide, we've got that coefficient of 2 in front. So there are two sodiums that will be in that solution. It's aqueous. And there are two hydroxide ions, and that also is aqueous. I'm running out of room, so I'm going to go to the next line. Oops, and I need a 2 in front of there as well. Now, on the product side, the only one that I split apart is the one that's aqueous. And if you look, the one that's aqueous is sodium sulfate. And in that compound, I'm moving right below. Moving here, kind of continuing on, moving right below, I'm going to form two sodiums because there are 2 in sodium sulfate. I'm writing aqueous, and I'm again including that SO4 -2 ion, aqueous. We do not split apart the water because it is not aqueous, it's not dissolved in water. So I'm going to write 2, and now I'm going to write it as H2O, as my liquid. Now if we remember, when we write out our net ionic equation, we remove what we call the spectator ions. They are the ions that simply don't take part in the reaction. They exist in the same form on both sides of the equation. So looking at this, first off, I look at my H+. I've got an H+ on my reactant side, but I don't on my product side, so H+ is not a spectator ion. SO4, however, I have SO4 with a -2, and it's aqueous on my reactant side. And now on my product side, I also have an SO4 -2. Those two are both in the same form. They are spectators. The other spectator ion is the sodium +1 ion. So removing those, I simply write out everything that's left over. I've got 2H+, aqueous, plus 2OH-, aqueous, makes my only product that would be left over is the 2 waters. And my liquid. Now, is this in the lowest reduced form? No. We'd write it out, H+, aqueous, plus OH-, aqueous, makes water, liquid. And this technically would be the right answer. And this would be the same exact thing every single time we react an acid and a base together.